Now you got the PDF of the book, right? Huh. And that book has all the reference you ask you were asking that day. So all the reference are there in the books. So if you go through the book, you will see I am basically follows that book, and here and there I will also follow the non-linear that other book by Strugach. So let's begin today's class. So we will talk about periodic orbits. So previous in the previous class we have learned what is a period, what is a orbit. So we know that if there is an suppose a initial condition, suppose x0, and if I iterate it through a map f, then the collection of the iterate, suppose it will go to x1, then it will go to under the iteration x2, and so on so forth. Then the collection of these points x0 x2 x, suppose this is x3, so collection of these points is called orbit of x0, orbit of x0 under the map. Now let us see which is what is a periodic orbit. Now we will use this concept orbit to mathematize the concept periodic orbit. Now why we are interested in periodic orbit? Because we know, as we will see in the later on, that in the to for in a system, if you want to see chaos, the periodicity is very essential, because in the definition of the chaos, how you define the chaos, there you need a dense periodic orbit. So that's why to introduce what is a periodic orbit is very crucial for serving our purpose to know the chaos. Now other than that, in our daily life, everyday life, the periodicity is everywhere. So suppose that in migratory bird, in the migratory bird, during the reproduction, and due to reproduction they travel to the same spot every year, and they after reproduction they will go back to the original place. So this is a kind of periodicity that they are following. So you can think of it as these birds initial nest place is my this x0. Now under the map, and you could think the map here is reproductory purpose, under the map reproduction, they came to some other place, now after the reproduction complete, and it is a part of the reproduction and rearing the children maybe, so they go back to their original space, original suppose this is x1, suppose this is x1, this is x0. Now after reproduction, so if I apply a map called reproduction or reproduction and rearing children, so the bird's initial position change to some other positions. Then if I again apply the reproductive success, and they will again go back to their initial nest position. So this is kind of repeating it. So not only that, if I see to the sky, you will see that the sun every day, sun rises and sets every day. So that's also periodicity. And every time we will see around our daily life, we will see periodicity. As for example, suppose I have to wake up in the morning and take a bus from Monday to Friday. So I have to take a bus from my room to go to the institute. So here in case of mine, so suppose initial condition x0 will be my room. Now a function will be a bus this is function, it will take to me to the K institute. So x1 will be my institute, and after 4 or 6 p.m. I have to again take a bus and go get back to my room. So I have again, if I iterate my these x1 position by my institute position by a bus is a function which what will do this function, this function will take me from my institute to my room. So if you see, this is kind of periodicity appearing in our everyday life. So that's why let's mathematize the concept, or in case of mathematics, so let's define what is the periodic orbit is in terms of map. So let us define the periodic orbit or periodicity in terms of map. Now to know the periodicity, or to know the definition of the periodicity, we have to define the fixed points. So later on, means in this lecture, later on you will see, from these fixed points actually we will come to the definition of the generalized definition of the fixed points is actually the definition of the orbit, or the periodic orbit. So let me define first the fixed point. As its name suggests, it fixed points means it remains. Suppose there is a point x f or x star, x fixed, and it remain fixed. It remain fixed under the under the map f. So how many times I will iterate this function f to under this function, it will remain in the same remain fixed. So it will not change by the action of this map. So this is called the fixed point. Now let me define it mathematically. So as we know, we define this function as 1 to 1. That means if f is a function, it will map certain suppose a certain range of values to a certain range of values. In case of population dynamics, we know that this S is nothing but is between 0 to 1. So it's a closed interval between 0 to 1. So nothing but an f maps to another closed interval which is also a 0 to 1. So that's all. So a map, a fixed point of a map is a fixed point of a map is defined as, if suppose I take any value, suppose any value x from here, which has to belong to the domain of this f. So it is called domain, as we know that it is called domain. So if I take any x and it belongs to the domain, now this point is called fixed point if under the operation x or under the map it remain same. So that's, so if here you will see that if I operate the x with the function f, I will get back x. So that means the action f, under the action f, x remain fixed. That's why it is called the fixed point of this map. So this is called the fixed point of the map. So that is called fixed point. So if I draw it pictorially, so it will be like that. So suppose here I have a point. So under the map f, it will come to this point again, or you will say that this point is nothing is not changing at all. Now the question is why it is important. So as we know it is important, we have seen a glimpse of it. It is important because in case of the population growth model, we we uh, we calculate, we derive these equations which actually mathematize the discretize the population, or these the population whose have a preferred breeding season. So that is xn plus 1 mu into xn into 1 minus xn. So that mathematize a growth of a population who who prefer breeding in a particular season. So that's it. Now we seen that when these means the population cannot fluctuate infinitely, means if my resource is not fluctuating, if I continue, means if I the suppose there is a bacterial suppose there is a bacterial population, and if I supply resource at a constant rate, suppose I give them a resource at a particular rate, then since they have a constant amount of resource, so since the resource doesn't contain any fluctuation, and if I consider there is no other influence on the population on other things, then the population cannot be changing forever. So it should be rested on something. So that's it. So when it will where it will go, so we know that it will go towards that point, towards these fixed points, means it will go toward a point which will not change further in time. So and we see that means xn plus 1 is nothing but the iteration of the point xn. Now it says that this dynamics will go towards a fixed point, that means xn plus 1 become xn, because, and that means that xn is does not changing if I iterate with f. So that is basically the definition of the fixed point. So these points will be called the fixed point, as this point is called the fixed point. Now let's give me an example how to calculate the fixed point, then it will be clearer. Suppose I have a map. Suppose I have a map f, which suppose map 0, 1 interval into 0, 1 interval. So that maybe it's 0, not 0, 1, it's some other. Suppose it maps real line to real line. Real line means it could be minus infinity to plus infinity, real line to real line. Now this map is, suppose f of x will be x square minus 2x minus 4. So if I put some initial condition, so it will give me, suppose if I put any initial condition under the map f, it will go towards under the point x1. So f equal to f x1, f x0. Now what will be its fixed point? Now I have to find a point x0 which will remain x0 under this function. So that means if x0 or fx is a fixed point, so xf will remain xf under the action of xf. Now if I solve this equation, so that means is xf equal to xf square minus 2xf minus 4. Now if I solve this equation, we will get the value of xf. Let's see what is the value of xf. So xf square minus, it will be 3xf minus 4 to 0. So this is like xf square minus 4xf plus xf minus 4 equal to 0. So this is xf minus 4 minus or plus 1 minus 4 equal to 0. So this is basically xf minus 4 into xf plus 1 equal to 0. So this is either xf minus 4 equal to 0, or so let me write it, either xf minus 4 equal to 0 or xf plus 1 equal to 0. So the fixed point is either xf equal to 4. So if I put 4 in this function, this map, it will return me 4. I will check it. And if I again, or if I else I put minus 1, it will give me minus 1. So let check whether it is giving back the value or not. So let me put first 4. So f of 4. So that will be x square first of all. So this is 4 square minus 2 into 4 and then minus 4. So it will be 16 minus 8 minus 4. So this will be 4. So yes, indeed it is true that this is a fixed point of this map. And again let me put minus 1. So minus 1 its square minus 2 into minus 1 and minus 4. So this will be 1, this will be plus 2, this will be 4. So this is again minus 1. So yes, indeed the minus 1 is the fixed point of this function. Subhudaji, do you have any question about regarding the fixed point? Hmm. 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 Oh, so here from in this equation you will see that xf, if I want to find, so I have to solve this equation. So xf equal to xf square minus 2xf. Now if I take this xf this side, so I have to subtract xf in the both side. Now if I subtract okay, that's it. So that is the definition of a fixed point. So what is the definition? Let me write it. So if x is the fixed point of a map f, then x has to satisfy this equation. Then I will call x is a fixed point of f. Now if you see the example of my daily routine, so if I take that classic example of my daily routine, that means every day at 10 I have to leave my room, and my position under the action bus, under the map bus, it will go to a institute, and after again if I apply a function in bus to institute, I'll reach back to my room. So you see, if anyone observe me, suppose if anyone, my neighbor observe me at suppose 8 p.m., 8 a.m., 8 a.m. and 8 p.m. Suppose any neighbor of mine just came to my room and to say hello to me, then if they came at 8, if every time they come at 8 every day 8 p.m. and 8 a.m. and 8 p.m., they will see fixed me in the room. they will see me, I am not leaving my room at all. So they will see that room, my position is room is fixed, not the position of my mind is not changing, it is remain fixed, fixed room. But you see, I my position changed during this 8 p.m. to 8 a.m. to 8 p.m. to one time. So that means, see, this position room is a fixed point if I operate operate my position with consequently two function called bus. So if I first apply the if I first take the bus, these if I take the bus as a function, then it will take me to the institute, and if I again take me the bus, it will get me back to my room. And that's why my neighbor find me room in every day 8 a.m. and 8 p.m. That's why they in their view it is my fixed positions. So that means my position, that room, is fixed. Suppose bus is a function and room is my initial condition, it will remain same. It will first will go to institute. If I again applied bus in this, so if I bus applying bus here, so it will get me to my room. So you see, and in the previous class we have seen that this is called the composite function. So if I iterate a function two times on a single initial condition, so if you see here I am applying or I am iterating by bus my position two times, then it will be, I can write it in this way. So bus, if I two time applied bus to room, it will uh, so so it will become room. So now you see, so why my neighbor find room is my fixed point, because my room is actually a fixed point under my room is a fixed point of the function that bus 2. So that's why this is called a fixed point if I applied the bus consecutively two times. Now you see, this is a fixed point, but if you see from the position room, you will see this is a periodic orbit. So from room to institute, then institute to get back to room. So that means if I say so, then I can think of that this is a periodic orbit of periodicity 2. So this is a 2 period orbit, we can think is a my this suppose this is then what is the orbit here? Orbit will be room to bus, room to institute. So let me write it. What will be the orbit? What is the orbit here? Orbit will be room to institute, again room to institute, and so far so on. So this is my orbit. Now if you see the orbit is repeating itself, room to institute, then institute to room, again room to institute, institute to room. So this is look like a periodicity. Look like a periodicity. Then we can say that, so periodicity of period 2, so 2 periodic orbit, we can say this is a 2 periodic orbit. Periodic orbit. So because why 2 periodic orbit? Because here in the orbit it contains only 2 points which infinitely repeat itself. So if I now generalize this idea, then we can think that the fixed point of f the fixed point of the, okay, let me write it in this way, the fixed point of second iteration of a function is called two periodic is has no, the fixed point of the second iteration can be called the fixed point of the second, okay, let me, if suppose, let me tell you in this way, suppose uh, so suppose x is a fixed point of the second iteration of function f, second iteration of function f, that means f2x equal to x, then the orbit of x under f, not f2, under f, is the periodic orbit of period 2. So if I, so this means if I applied suppose f to x0, it will go to x1. Now if I again x0, it will go to f of x1 into x0. So if I draw pictorially, it will look like, so suppose here it is x0, suppose here it is x1. So first of all it will go to f x1, then it will go back to x0. So this is a periodic orbit. So that is called a periodic orbit of period 2. Subhajit, did you get this concept of periodic orbit? Okay. Hmm. Hmm. Yeah. Two fixed point, yeah, it is two fixed point of if I iterate two times by bus. Suppose if I iterate two times by bus, the position institute will remain the institute. So that's why that is called the fixed point of the second iteration of the, if I iterate the position two times consecutively, the position will remain same. That way, that why it is called the fixed point. Now that's it. Now this is the fixed point. Now let's generalize the definition furthermore. So suppose if I iterate a function, iterate a initial condition or a position x0 n times, and okay, let me write it. Suppose that x0 xf is a fixed point of the nth iterate of the function, then xf will be called the xf will be called obviously fixed point. It is exactly the fixed point, because if I iterate the xf n time, then it will remain fixed. So that's why it is called fixed point of nth iterate of f, and xf will be also called, if I go back to this example, so since it is a fixed point of second generation, we can, if I applied f two times, I will get back, reach back to x0. So that's why it is called a periodic orbit of order period 2. Here again, if I generalize that idea, we can call xf the orbit of xf, the orbit of xf is a periodic orbit of period period n. So that's all. So it basically says that if suppose this is my space, now if suppose there are n points here and there, so it says that under the f, first it will go to here, then it will suppose x1, x2, x3, x4, x5, x6 dot 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 xn. So it says that x1 to x2, then x2 to x3 it will go under the map f, then x3 to x4, then x5 and so on, and now it will go to xn. Now again if I nth time if I applied the function, suppose it is xn minus 1, so if I apply the xn, I will get xn by applying map xn minus 1. So you will see that this xn will become x1. So you will see this xn will become x1, and you will find that x1 or x0, you will find that x0 equal to nth iterate of x0. So then we will call this x0 as the orbit of x0 under the map f is the periodic orbit of period n. So that's all. Now another thing I want to show you, that an example. So suppose, so it's an abstract example, and so these point, so this is x0, this is x1. So under the map, suppose this is f, under the map x0 comes to x1. Now x1 will go to x0 under the again map f. So what will be the orbit of x0? So orbit will be, so it orbit contains x0, then if I iterate f, I will get x1, then again x0, then again x1. So this is one orbit. Another orbit we will get, which will be, suppose x1 from then if I apply the map, it will give me x0, then again x1, then again x0. So you will see I will get two different orbit. So two different orbit if I start from two different initial conditions. If I start, suppose if I start from my room, so that will be, I can write my room institute, that is a period. And if I start from my institute, I will again can write a orbit, that will be institute, my room, institute, my room. So that's all. So that is basically two different orbits. Now if I generalize this idea in the same manner, so if there is a n periodic orbit, then I have n different kinds of orbits. So if I n periodic, let me write it. So if I generalize, if I n a point which is n a orbit whose period is n, or it is called n periodic orbit, period n point, or it is called the period n point. So the technical term or mathematical term for this is xf. Xf will be period, period n point of f. So if I have a point which is xf, which is suppose period n point of f, then I will have n different orbit. So you will see that here there is n different points. So if I start suppose x0, I will get a one orbit. If I start from x1, I will get another. If I start x2, I will get another. So there are n such points. So I will get n different orbits. So that's all. So that is basically the period. So now let us give you an example. Not example, okay, I will show that later. So now another thing I will want to show you, that is another again a definition. So because we want to know this definition, because whenever we will get deeper into this subject, we will use these jargons here and there. So that's why we need to first clearly have an understanding what this word means. So this is called the eventually periodic orbit. This is called eventually periodic orbit. So now if I get back to that my room and institute example, now I am in IISER Kolkata. Now if I also take account of my IIT days, so from if I start from not from here room near about IISER Kolkata, if I start from my hostel days of IIT Kanpur, so if I start my fixed point from IIT Kanpur, then from IIT Kanpur, if you see my today's positions, if my neighbors know that I am from IIT Kanpur, then they will find that no, there is a change. Although I every day I remain in my room, I remain fixed in my rooms, but there is a history that I came from IIT Kanpur. No, so this is called the eventually I came to IISER Kolkata, and I choose such room that my everyday routines become periodic. So it is called the eventually. So you will say in mathematical terms, my daily life routine eventually become periodic. So this is called IIT K to suppose my room. So I am every day I am not get back to IIT, but my room to in IISER K, and then again from IISER K to my room. So if you see start from here, you will say eventually I to reach to a lifestyle or life routine. Their life routine has a periodicity. So that is called basically periodic orbit. So in terms of in mathematical terms, so eventually periodic orbit point, suppose again f is a function which map s to s, is a domain and is a codomain. A point x0 belongs to s is said to be an eventual periodic point of f if some iterate of f xk, suppose here, so here again I can take this function bus. So from IIT Kanpur, if I took a bus or anything, so not bus, it will be train, so forget about those details, but we could think it is a position, and if I take a bus, so if I take a function, so suppose it's x0, so that this function, the bus take me from x0 to x1, and here this bus taking me towards a fixed point, towards a point x1, which will be a 2 period point of this function, or this x1 will be a fixed point of the second iterate of this function. So here also, if we generalize this idea, then I am saying that, so if there is a point, and if the sum iterate here, suppose that the first iterate of the IIT K take me to my room, so here if some iterate of f takes this fixed point to xk such that xk is a periodic point of f, then x0 is called, x0 is said to be, okay, then x0 is said to be eventually periodic point. So eventually this x0 will go towards the point x0 through the iteration. So from, suppose, let me write it in this way, it will be clearer. Suppose x0 goes to x1, then x2, and so forth, so on, and it will get to xk. Then under the xk, suppose xk plus 1, xk plus 2, and then get back to xk. So eventually this x0 reach towards the point which is a periodic point of f. So this is called the eventual periodic point. So let me give you a mathematical example. So suppose that so that the 1 plus root 3 is an eventual point of mapping. So previous map fx equal to x square minus 2x minus 4. So to be a periodic point, I have to, these points have to reach to a point which is a fixed point of this, because we know that the periodic point is nothing but a fixed point of some kind. So if fixed point of nth iterate of fixed point, so if it become the fixed point of first iterate, suppose x0 will remain x0 forever, so we can think like that, that is a period 1 point. So that means we have to show that, or let me put it here, so then it will be more clear. So 1 by root 3, 1 by root 3 square minus 2 plus 1 minus 4. So this will be 1 plus 2 root 3 plus 3 minus 2 minus 2 root 3 minus 4. So these will be cancelled. So 3 plus 1 4, and minus 4, it will be cancelled. So it will be minus 2. Now if I applied f of minus 2 again, so this will be minus 2 means 4, minus 2 into minus 2 minus 4, so it will be plus 4. So and we know that if I apply plus 4 on this, it will remain 4. So it will do that, it will be eventually a periodic point. So first 1 by root 3 to go to a point minus 2, then it will go to a point which is 4. So under the map f, this go to this, and then under the map this minus to go to 4, and if I apply minus f here again, minus 4 to 4. So this is a period point. So since 4 is equal to f of 4, so this is a period 1 orbit, or it is called, because it is trivially it is a fixed point, it is called period 1 orbit or fixed point. So that's it. That's all. Now let me another thing. So this is pretty much all this is, but I want to move two things today. One is now since you see that to calculate, to see the periodic orbit of a map or periodic points, I have to find the fixed points. So find the fixed points of a map. So it is here in the previous case, it was very simple example, so that's why we can able to calculate its fixed point. Suppose here, so here it is very simple like quadratic equation, that's why it is very simple to calculate its fixed point, but it will not be the same forever. So now let me before going to that, let me ask you that question, that if is it clear that what is eventual periodic orbit, Subodhaji? Right, right. Uh, yeah, yes, that's it. So in the next classes we will see that we will see that the some initial conditions, if I put suppose that a system, when we will say that the system's fate is a periodicity, then we will say that wherever you will start, that point, initial point, eventually go toward the periodic point. So those kinds of jargon we will use later. That's why we are interested in these definitions. That's it. So let's see how to find a fixed points of a map. So if I give you an example, hard example, suppose we know that our logistic map, suppose this is mu equal to, suppose mu equal to 3.1 or something, xn 1 minus xn. So you can write it xn equal to f of xn, where f of xn can be written as this form, mu xn 1 minus xn. This is that. Now if I ask you to find the fixed point of second iterate of f, that means x square, or since we know the fixed point of the second iterate is, or is a period 2 point of f. So can we find the period 2 point of f, which is equivalent to say that the fixed points of the second iterate of f. So to find that, we know we have to satisfy this equation. Suppose x0 is the period 2 point, so then x0 has to satisfy this equation, because after iterating 2 times f, it will reach back to x0 again. So if I, that means my equation will be look like x0 will be f applied on f of x0. It means I know f of anything will be mu into that thing into 1 minus that thing. So f of x means mu into Subhaji, can you guess what will be this? So it will be, if I applied f on f of x0, what it will be if I follow this definition? Okay, let me write it, then it will be clearer. So yeah, it is little bit confusing, I know. So it is mu, then since I applying same to here, it is this, suppose this is x1, not a f x1, suppose x1 equal to f of x0. So here it will be, let me write it in this way. So we can write it f of x1, and what will be f of x1? That will be nothing but mu into x1 into 1 minus x1. Is it clear, Subhaji? Then it is meaning mu of x1 is nothing but f of x0 and 1 minus f of x0. Subhaji, is it clear that? Then let me write it in this way. X0 should be equal to mu, and f of x0 means we know that again mu into this is x0 into 1 minus x0. Here this means, and 1 minus this means minus mu into x0 1 minus x0. Now you see that this equation look horrible, and mu square x0 1 minus x0 minus under this mu cube x0 1 minus x0 square. So you see this equation cannot, means it can be solved by hand, but it is tedious to do so. It is very tedious to do so. So that's why we generally use a method which is called the graphical method. It is called graphical. So to solve any equation, this is an example. So to solve any equation, suppose, so you can think this f second generation of f is a function gx. Suppose you can solve any function like this by graphical method, in which what we will do, so we will do basically in the 2D plot, in the 2D graph, if suppose this is x and y is gx, first we will plot this gx. Suppose the gx is in this way. Now I have to find the solution where the gx become equal to x. Now if I draw a line which is a y equal to x, so if I draw a line, so a line will say that it will connect every point where y will become y is become equal to x. So if this is my y, so this line is join those points whose x coordinate is same as y coordinate. So if suppose this is x, suppose then this is suppose a prime prime, so this is x prime y prime. So I draw, means we have to draw a line in such a way that x prime become y prime, or y prime is equal to x prime. So if I know x, so if I put the same value here, we will get this line. So this is, if I draw this line, now this is the line y equal to x, and this is the line x, this is the line y equal to gx. Here this is the y axis, this is the x axis. Now you see where this blue line and the red curve cross each other. So this point is this point. Where they cross each other, what is that point? Since I know every point on the y is same as x, so this point says that in this point, we know from the definition of this y line, we know that in this point the y is same as x. So thus in this point you can see the and we see that the y of this point is same as the y of this red, y of red is equal to y of blue, because this is the same point, right? This point is same. I don't know what happens. Okay, let me rejoin it. Hi Subhuja ji, can you hear me? Okay, so this y of this red curve is same as the y of this blue curve. So from here we know that, and we also know that from the blue curve this y is same as x. So we can see that, and here this red y, we know the red y is actually gx. So from these equalities we can see that gx is equal to x in this point. So then we can solve. Oh, okay, fine, no problem. Okay. Now you see that Now you see this y, they where they this blue line and red curve cross each other. Suppose this point is x comma y. So now you see the y of red curve is same y of the blue curve, and from the blue curve we know that this y is equal to x. So if I follow these equalities, the gx will be the y of the red curve. If I know the x, then the gx will be the y of the red curve. And since the y of the red equal to y of the blue, and since the y of the blue is equal to x, so we can form, if I follow this logic, then we will say that gx equal to x. Then I can say that gx equal to x at this point. So now we see that this point is the solution of this equation x equal to gx. So that's why if I know the value, what is the coordinate, what is the value of x here, so we can tell that what is the solution of this x equal to gx equation. Did you get it? Do you get it? Subhaji? Graphical method of calculating fixed point. Are you there, Subhaji? Okay. Huh. Yeah, I can hear you. Continue. Yeah. Yeah, right, exactly. So in the, since now if I apply these things, I can use my computer to apply a brute force to calculate that particular solution. Now in the next class we will see how to using a computer to solve this kind of equations. And I also see quasi-periodic orbit, but I plan to show you quasi-periodic orbit in this class, but it past 12, so let me show you it in the next class. Okay, so if you have any question, you can ask me, or we can leave this meeting here. So it's already, I don't know, my okay, so Pusaji, if you have any question, you can ask me, or let's end this meeting here, or I will, since it is past 12, I have other work, so let's meet in the okay, next class. Okay, thank you for joining.